Fibonacci numbers is a sequence of natural numbers that appears in some applications. For instance, we find this sequence in biology, in botanics, for example, in mathematics, of course, and in particular in geometry and many other situations. Here, we will introduce this sequence through a simplified model for the study of the evolution of a population of rabbits. We will assume three basic hypotheses, which are the following. The first one is that initially, so at the initial time, there is just one pair of rabbits, and this is a pair of baby rabbits. Then, second assumption is that each baby pair of rabbits grows and after 1 month is mature to reproduce. So they mate, and the month after they generate a new baby pair of rabbits. We assume that these three rules, these three laws, are valid forever. So for instance, we do not consider that rabbits could die. And also we assume that this reproduction mechanism works in the same way perfectly forever. So for instance, this means that a mature pair of rabbits cannot generate 2 pairs or 0 pairs or even 1 rabbit or 3 rabbits. Just 1 pair of newborn rabbits, male and female, each month. So as you can see, it's a particularly simplified description of how a population of rabbits could evolve. Now, to see how these three rules works in practice, let's imagine a graphical representation of this situation. So initially we have a pair of baby rabbits. After 1 month, this pair is now an adult pair of rabbits. They mate, and the second month they will generate a new pair of rabbits. Now, the next month, this pair will continue to generate a new pair of rabbits, which is here, while this pair will just grow and become mature. At this moment, we have 2 mature pairs of rabbits, so they will generate each a new pair of baby rabbits. So this is the pair generated by the first one, and this is the pair generated by the second one. While this baby pair will be just growing, aging, and it will become mature at the next month. So now we have 3 mature pairs of rabbits. They will generate each a new pair of baby rabbits. And so after, in the next month, we will have these pairs of rabbits. If we count the pairs, so if we call Pn the number of pairs at the end month, we have that at month 0, so initially we have just 1 pair. After 1 month, we have still that pair that has become just mature. After 2 months, there are 2 pairs. After 3 months, there are 3 pairs, then 5 pairs, then 8 pairs, and so on. Of course, the principal problem is can we describe how the number of pairs, Pn, depends on n directly? So to do that, we need, first of all, to start from an equation that can represent the value of Pn. Now, according to our model, the number of pairs at month n can be computed in this way. First of all, there is the number of pairs which are alive the month before. They will still be alive because we do not consider mortality. And we have to add to these pairs the newborn pairs. And how can we compute the newborn pairs? Well, the newborn pairs are generated by pairs that were alive 2 months before, because 2 months before you have a certain number of pairs, mature and babies. The month after, which is n month n-1, all these couples will be mature, and each of them will generate a new couple. So the number of couples at time Pn-2 coincide with the number of newborn pairs at time n. So this is an equation. We call it equation because it is an identity where the quantity Pn can be considered as unknown. And the first question is, can we determine explicitly the value of Pn? And in particular, can we say anything about the long-time behavior of this Pn? So for instance, we see clearly that this quantity Pn is rapidly growing. But how is growing? Is that exponentially growing? So is it possible to have that Pn is an exponential? Now we can answer to this second question, and this will, as you will see, give the answer to the first question in some sense. So imagine that we start from a Pn which is of exponential type, and we wonder if this kind of sequence can be a solution of that equation. To be a solution, we just plug into the equation. So this is a solution if and only if we have Pn, which is a to power n, equal Pn minus 1, which is a to power n minus 1, plus Pn minus 2, which is a to power n minus 2. As you can see, we obtain a sort of equation for the number a. Clearly, this equation is verified when a is equal to 0. And this can be considered a trivial solution because a equals 0 means Pn constantly equal to 0. So there is no evolution. There are 0 couples initially, and this will be forever. We can call this a trivial solution of that equation. So if we assume that a is different from 0, so if we look for a non-trivial solution, we could take this identity, this equation, and divide everything by a to power n minus 2. What we get here is a square equal a to n minus 1 divided by a to n minus 2 is a, and this is plus 1. As you can see, this is a second degree equation, a squared minus a minus 1 equals 0, whose solutions are a plus minus equal minus 1 plus minus the root of 5 divided by 2. Plus 1. Plus 1 plus minus root of 5 divided 2. This argument found two particular solutions to the Fibonacci equation. They are the two exponentials a plus power n and a minus power n, with a plus a minus given by this formula. For a plus, 1 plus root of 5 divided 2. For a minus, 1 minus root of 5 divided 2. We may wonder if one of these two represents the Fibonacci sequence representing the couples of rabbits according to the model we described at the beginning of this video. Unfortunately, the answer is negative, and this can be easily seen because even if for both you have that P0 is 1, you can see that P1 is not 1. Remind that the number of couples of rabbits at the first generation is just 1. And here we have P1 equal one of these two numbers, which are not equal to 1, and they are not even rational numbers. They are irrational numbers. One can prove that also these numbers are always irrational numbers. So in other words, they seem to be very far from the sequence of Fibonacci numbers, which is a sequence of natural numbers. So we may wonder if there is a way to use these solutions to obtain the Fibonacci sequence. And that's possible thanks to the following remark. It is possible to prove that if we take a linear combination of these two particular solutions, we have a solution of the Fibonacci equation. What is a linear combination? A linear combination means that we take a sum of multiples of the two solutions, let's say roughly. Something like 3 times the first plus 2 times the second, or 5 times the first minus 7 times the second. We can take any combination with the coefficients lambda and mu taken arbitrarily in reals, and you can prove that this Pn, constructed in this way, will always solve the Fibonacci equation. I invite you to verify this. It is not complicated. You have to use, of course, the fact that a plus to power n, a minus to power n, they are both solutions of the Fibonacci equation, and then you will figure out that also Pn is a solution of the same equation. Now this tells that actually there are not only just these two solutions for the Fibonacci equation, but here we can see that there are infinitely many solutions. For every couple lambda mu, we have a different solution. So we may wonder if for a suitable choice of lambda and mu, we can find our Fibonacci sequence of natural numbers that we presented at the beginning of this video. Now, to do that, we must impose two conditions at least, which are P0 must be 1 and also P1 must be 1. Conditions that are not verified, for example, by these two solutions. Now, if we impose these two conditions, we easily see that this can be translated into a system of two equations into two unknowns, lambda and mu. In fact, for the first equation, P0 equal 1, when we set n equal 0, we obtain lambda plus mu equal 1. And when we take n equal 1, this becomes lambda a plus mu a minus equal 1. As you can see, we obtained an easy system of two equations into two unknowns. This system is a very simple system because it's a linear system we can easily solve. I invite you to write down the solution. And once you find out the values of lambda and mu and you plug into this formula, you will see that the Pn will assume this form. Pn equal 1 over root of 5 times a plus to power n plus 1 minus a minus to power n minus 1. Now this is the Fibonacci sequence because once the first two elements of the sequence are given, all the remaining elements are automatically determined by the law Pn equal Pn minus 1 plus Pn minus 2. So these are the Fibonacci numbers. What is remarkable here is that 1 over root of 5 is irrational. These are irrational numbers, but nonetheless, this quantity is a natural number. So it's a little bit surprising fact. From this formula, we can also respond to the other question we posed, namely if Pn is exponentially growing or not. We can see here that apart from this factor, there are two exponentials, a plus power n plus 1 and a minus power n minus 1. They are pretty different because if you look to the first one, a plus is 1 plus root of 5 divided 2. Root of 5 is greater than 2, so that number will be greater than 3/2. In particular, it will be larger than 1. So this is an exponential sequence with base larger than 1, and therefore is a sequence rapidly growing. For the second part here, a minus is 1 minus root of 5 divided 2. Now this number is between minus 1 and 0. In absolute value is strictly less than 1. And therefore, this makes this quantity decaying rapidly to 0 because it's a number, let's say in absolute value less than 1 multiplied by itself n plus 1 time. So each time you reduce the size of the product. So this means that when n is big, this second number becomes, let's say, negligible with respect to the first part. So we may say that if we have to look at this quantity when n is big, this is approximately equal to 1 over root of 5 a plus to power n plus 1. So this means that practically Pn grows exponentially, and it grows exponentially like this exponential.